The last major class of chemical reactions that we're going to talk about are ones involving electron transfer. And for short, we tend to call these redox reactions. But for long, we call them oxidation and reduction. So let's take a look at an example, and you can kind of see what I'm talking about. So a really great example of this is if we have silver nitrate, and we add in a piece of copper wire, for example, then what happens is silver nitrate is a clear and colorless solution, and as soon as you put the copper in, the solution starts changing color and it starts turning a little bit blue-green. And what's happening is that the copper, which is currently in the form of a copper wire, starts turning into copper nitrate. And at the same time, you'll see these little needles start to form on the copper, and that's silver metal that is solidifying on the copper wire. I'm going to link a video showing this reaction for you so you can actually see it happening. So you can take a look at that outside this video. All right, so in this chemical reaction, if we look at what the chemical species are, here we have silver nitrate, and the silver is starting out as an ion. We have Ag+. And over here we have copper, and it's just metal. It's not an ion. And then it turned into, the silver turns into silver metal, not an ion. And the copper turns into copper 2+. So that's an ion. So we have this change. And so both of these are now switching from being part of an ionic compound to not, or vice versa, not in an ionic compound and now part of an ionic compound. So if we took a look at what the net ionic equation for this was, and if you need practice, then pause the video and write out the complete ionic and the net ionic equations. So if we look at this, we'll get 2 silver ions react with 1 copper in solution to make a copper 2+ and 2 silver not ions. So what we can see from this here is that we have electrons being transferred. All right, when this silver goes from being silver +1 to the solid metal, it picks up an electron, and of course, since there's 2 silvers, that's 2 of them. And so we would say that silver is reduced. So when you gain electrons, that is called reduction. And we can see this happening because our ion charge here is going to be less positive if we gain electrons. And we'll talk more about that in a second. So here we can see that when copper goes to copper 2+, it loses 2 electrons. And we would say that copper is oxidized. So when we lose an electron, or multiple electrons, we call this oxidation. And we've got a couple of mnemonic devices, memory aids, if you need them in order to remember. So oil rig is one of those. And that would be oxidation is loss of electrons, and reduction is gain. Or the other one that I have heard is Leo Ger, which I find a little bit contrived, but it's loss of electrons is oxidation, and gain of electrons is reduction. So whatever you need to do to remember which one is loss and which one is gain, go ahead and do that. So oxidation and reduction always happens together, because if something is losing electrons, those electrons have to go somewhere. And if something is gaining electrons, those electrons had to come from somewhere. So this oxidation and reduction is always happening as a pair. So they must happen together. You can't just generate electrons out of nothing. So I like this example because it's so clear from looking at this reaction that you have a silver ion that's turning into metal and a metal turning into a silver ion, that it's super clear. But many oxidation reactions, which we will, as I said, often just call redox reactions, are much more subtle. And so in order for us to identify them, we need to be very specific, and we need to be able to learn how to identify oxidation numbers. That doesn't start with a Q. Oxidation numbers. All right, so let's take a look at that reaction again, and let's talk about oxidation numbers and ion charges. All right, you can already see some ion charges, right? These guys are ion charges. And this also is the oxidation number. So for monatomic ions, like silver and like copper, the ion charge equals the oxidation number. But what about this just plain copper or just plain silver? You know, these aren't ions, they're metals, they're also pure elements. And for all pure elements in their elemental form, these are considered to have an oxidation number of 0. So if I were labeling oxidation numbers for each of these elements, I would write a +1 over the silver, I would write a 0 over the copper, I would write a +2 over the copper 2+, and I would write a 0 over here for the silver metal. Okay, so these are two of the rules, and we have a set of rules for oxidation numbers and for figuring them out. In our book, you can find them on page 185. I'm going to talk about them in a slightly different order than the rules listed in the book. So these are technically rules number 2 and 3. And this is actually rule 2, and this is rule 3. Okay? So the next rule is how we would deal with figuring out what the ion charge for the nitrate was, right? Because we have silver nitrate or copper nitrate. And so we already know that this is Ag plus and NO3 minus. And we figured out that the oxidation number on the silver was a +1. But now we have this whole big unit here, and it combines both the nitrogen and the oxygen. I usually do this rule last, but we'll go ahead and jump right in. This is the rule number 1 in our book, which is that the oxidation numbers of a neutral compound must add to 0 and of a polyatomic ion they must add to the ion charge. So let's take a look at an example of this. Let's look at something like sodium chloride, which we're really familiar with. Again, we know that sodium is really sodium ion and chlorine makes chloride. And so because of that, our oxidation numbers are just going to match the ion charges here. So the sodium will be a +1 and the chloride will be a -1. And if we add those two together, +1 plus a -1, that's equal to 0. And notice that we have no net charge. This is a neutral compound. And so that's why they have to add up to 0. So now we're ready to look at nitrate. And the reason why this really is a rule that I do later usually is because we need to know how to deal with oxygen. So oxygen is usually -2, which is going to be one of our later rules here. So it's going to be -2 in this polyatomic ion as well. So if we have 3 of these -2 charges and nitrogen, whatever nitrogen is, these have to add up to -1. So 3 times -2 is -6. And if we have nitrogen as something, it needs to be a number that if we add it to a -6, we get a -1. So nitrogen will be -5. And of course, if you want to do the algebra on this, then we would just add 6 to both sides. Sorry, I just told you it was negative. That doesn't make sense. Nitrogen is a +5 in order to make this true. So I would write that my oxidation numbers are +5 on the nitrogen and -2 on the oxygen. So notice I just list it for one element, one of that element. I don't say -6 over the oxygen because I'm just talking about each element and its oxidation number on an individual atom. Okay, so we'll use this rule a lot, but we need some other rules to tell us about how to deal with some of the other common elements that we're going to see. So I want to note here, just as sort of a sideline, is that most metals are ions, right? And so we're just going to look at the ion charge for whatever that metal is. And so it's mainly the nonmetals that have weird rules. So the next couple of rules, next 3 rules, are going to deal with the nonmetals. So the numbering on my rules here is the numbering in the book, and that's where it's coming from. I just wanted to make sure that was clear. So rule 4 is super easy. It's about fluorine, and fluorine is a very nice, simple element. It always has an oxidation number of -1. Well, I mean, okay. If it's in its pure elemental form, which would be F2 as a gas, then it would be 0 because it's a pure element. But anytime it's in a compound with something, so I'll put that here, if it's in a compound. Doesn't matter which element it's in a compound with, it's always going to be -1. No exceptions on that one. All right, so here's the next one. The next rule has to deal with hydrogen and with oxygen. And the rule says that the oxidation number of hydrogen is usually +1, and of oxygen is usually -2. We have exceptions. The exception for hydrogen is pretty straightforward. If hydrogen is acting as an anion in an ionic compound, then it will be -1. So here's an example. If you have calcium hydride, let's see. We know that calcium is always a 2+ cation, and so there is no option here except that hydrogen has to not be +1 here, but it needs to be -1 because there's 2 of them, and so each one will be -1 and they will add up to 0. So this pertains to that rule number 1. Okay, so that's the exception for hydrogen. The exception for oxygen, we actually have 2, but one of them is very, very rare. So one is if you have peroxides. So a peroxide looks like hydrogen peroxide, H2O2. You can also have sodium peroxide or potassium peroxide, and that's basically about it. So if you have one of those 3, then take a look. Hydrogen, we know, is usually +1. We know that sodium is always +1 and potassium is always +1. So what has to happen with the oxygen in this case? Based on rule number 1, we have 2 times a +1 plus 2 times the oxygens, and that has to equal 0. So in this case, when we have peroxides, then the oxygen has a -1 redox or oxidation number instead of a -2. The other situation, which you'll probably never see in real life, is called a superoxide. And a superoxide is a very weird compound. It mostly happens with these alkali metals, like it could be sodium oxide, except that we have to somehow indicate that we've got an O2 there, or potassium. I don't know, maybe we just have to cave in and say dioxide, I don't know. But anyway, take a look. We have a +1 here and a +1 here. What's going to be the oxidation number of the oxygen? Well, we've got a +1 and we've got 2 times the oxygen, and that has to equal 0. So I don't know about you, this is very awkward with, we'll make that one a 0. This is oxygen. So the oxygen needs to have a -1/2. That's very strange. You never see that in anything else. So this is the weirdest it's going to get. All right, so our last rule is rule number 6, and it pertains to chlorine and bromine. I don't know, maybe iodine sometimes too. So unless they are combined with oxygen or fluorine, the other halogens are usually a -1 oxidation number. But if we have a combination with oxygen or fluorine, we know fluorine is always -1 and oxygen is always -2, since these guys don't include the peroxides and superoxides with any halogens. So oxygen is going to be a -2 and fluorine is going to be a -1, and sometimes the halogens have to kind of deal. So let's look at a couple of examples here. If we have something kind of normal like calcium bromide, then we can see that the oxidation number on the calcium is +2 because that's the ion charge, and we have 2 bromines, and this is pretty straightforward, right? We know that the bromine is really bromide, which has a -1 charge, and so there we go, +2, -1. This would be normal. How about a polyatomic ion like ClO3- though? All right, let's take a look. We have 3 oxygens. Each of those has a -2. And then we're going to have a chlorine, and it has to add up to a -1. So just like we did with the nitrate, 3 times a -2 is -6, plus chlorine is equal to -1. So add 6 to both sides, and you'll get that your chlorine here has an oxidation number of +5. All right. Now, in order to identify a redox reaction, you're going to need to be able to identify these oxidation numbers. So as you can see, most of the oxidation numbers you can figure out based on ion charges, and this is another reason why you needed to be really solid on knowing all your ion charges. So if you're still working on remembering those polyatomic ions or how to decide what the ions are from the periodic table, please make sure that you're doing that. So let's do a little bit of practice before we finish up here. So go ahead and try these out. Try out carbon dioxide. Try out the permanganate ion. And try out iron ClO2 3. Okay, so pause the video and give these a try and see how it goes. All right, let's look at it, see how you did. So right over here, we have carbon dioxide. This is not an ionic compound, so carbon does not have an ion charge. So we need to go down our rule list, and we realize that oxygen is the one that's going to tell us. So we're going to use our rules for oxygen, which is that oxygen is a -2, and we have 2 of them. And we'll use rule 1, which says that the sum of the oxidation numbers has to add to 0 on a neutral compound. So we have carbon -4 is equal to 0. So that means that my carbon is going to have a +4 oxidation number, and those oxygens have a -2. All right, let's try permanganate ion. Oxygen again is a -2, and we have 4 of them. And then we have permanganate, which is something, and these all add up to -1. So manganese -8 is equal to -1. Add 7 to both sides, and we will get that the manganese has an oxidation number of +7. All right, over here to the iron compound. Now, let's check this out. We know that ClO2 has a -1 charge, and there are 3 of them, so that means we can already realize that the iron is going to have a +3 oxidation number on it. And now when we look at the ClO2, we're back to dealing with oxygen again. So we have 2 -2 oxygens plus a chlorine is equal to -1. So that's Cl -4 is equal to -1, and this will get us Cl is equal to +3. So we can label that up here, and we're done. All right, hopefully this has been a fairly straightforward set of rules for you, and that you won't have any trouble identifying oxidation numbers. Our next step is going to be to look at redox reactions, actively identify them, but we're going to use a lot of the same skills we've been using. So writing total ionic equations and net ionic equations, and we'll look at different kinds of chemical reactions.